Alright, section 5.2 is about annuities. So an ordinary annuity is a sequence of equal periodic payments where the payments are made at the end of each time interval. And there you're going to use the variable R to represent the amount of each individual payment. And we're going to be trying to calculate the future value of that annuity, which means the amount that will be in the account after making periodic payments over a certain length of time. Alright, so here is the formula, and we have the future value, we have R, which is the payment, and we have I, which is the same as it was in the last section, the rate divided by, the annual rate divided by the compounding periods per year. Okay, so let's see, if we want to find the value of this annuity, which means we pay $200 at the end of each month at 4.9% compounded monthly for 15 years. Okay. So that would be 200 times 1 plus 0.049. So we have, this is R, the payment, capital R, and then the lowercase r representing the rate would be 0.049. And since it's compounded monthly, M is 12, and then T is 15. So this is going to be 0.049 over 12. I think we're missing something on it. Alright, sorry, I think I accidentally erased this N that was supposed to be there. Alright, so to the power of, now remember N is going to be M times T, so that's going to be 12 times 15. Alright, minus 1. And then divided by I again, which is 0.049 over 12. Okay. So that should be it. Now we just need to plug that into the calculator. Alright, so if we're using the calculator on the computer, we have to make sure that we put actual multiplication symbol right here between 200 and that parentheses, because this calculator, unlike most of them, doesn't understand that the parentheses would indicate multiplication. So 200 times double parentheses 1 plus 0.049 over 12, close the parentheses, and then to the power of, open parentheses, 12 times 15, close the parentheses, minus 1, close the parentheses again, divided by, parentheses, 0.049 over 12. And that gives me $53,013.71. Okay. And let's see, this says round to the nearest dollar, but thinking on your homework actually rounds to the nearest cent. So let's just stick with that, rounding to the nearest cent. Alright. That's the total amount that would be in the account. And then to find the amount of the interest that was earned, we would just take that total amount and subtract the total amount that you actually deposited. So $53,013.71 minus, okay, the total amount of the payments would be $200, was the amount of each payment, times 12, since it's monthly, times 15, since it's for 15 years. Okay. Oops. Alright, so let's just put that in the calculator. Alright, so and remember, you know, we have to use the multiplication symbol on this computer calculator. So that gives us $17,013.71. So that's the amount of actual interest that was earned. Because this right here represents the amount of deposits. So if they asked you what was the amount that came from the actual deposits, you just multiply 200 times 15 times 12. Okay, so here's another example, same thing. Alright, so we're depositing $1,250 at the end of each year. So that's capital R, that's the payment. And then little r, the rate, is 0.0575. And it's compounded annually, so that means M is 1. And it's for 27 years, so that means T is 27. Alright, so future value equals 1250 times 1 plus 0.0575 over 1. And you really don't have to put the over 1 part if you don't want to, because dividing by 1 doesn't do anything. Alright, and then to the power of 1 times 27. So again, you don't really have to put 1 times, you know, the 1 times, so that doesn't do anything either. Minus 1. And that's all over 0.0575 over 1. Okay, so let's put that in the calculator and see what we get. Okay. Oops, forgot to put my multiplication. I'm not used to this computer calculator. To the power of okay. Alright. So $76,619.47. So the amount that came from interest, we'll just take that amount and then just subtract the total amount of the payments, which would be $1,250 times 27 times 1 we go to the calculator, $42,869.47. That's quite a lot. All right. And this is why Einstein said that compound interest is the eighth wonder of the world. Alright, so now we're going to do a couple problems where we find the amount of the deposits. So we want to know if we have a goal of saving up $250,000 over 19 years, how much do we need to deposit at the end of each quarter if we have interest that's compounded 6% compounded quarterly. Alright, so basically to do this we can use the same formula, we just want to rearrange it for us to solve for payments. So basically all we need to do is just divide both sides by this whole thing that's in the parentheses. Okay, so basically that formula would be payment equals future value divided by 1 plus I to the n minus 1. Oh, plus that's all over I. Alright, so that could be our formula. Alright, so R equals, okay, the future value that we want is 250,000. Okay, divided by, so we probably even need an additional set of parentheses around this whole thing. So we've got 1, 2, 3 parentheses. 1 plus, alright, so we've got little r, it would be 0.06, and since it's quarterly, m would be 4, and t is 19. So that's going to be 0.06 over 4 to the power of 4 times 19 minus 1 over 0.06 over 4. Okay. And let's see, I guess we need to close another one here. That should be it. And then we're going to plug that into the calculator. Okay, 1785.37. Alright. Alright, so if we want to know how much of the value came from interest and how much came from deposits, well, we can figure out the total amount of the deposits. $1,785.37 times 4, since it's quarterly, times 19. Alright, so $135,688.12. Alright, so that's how much that the person actually deposited, and then to figure out how much was interest, we'll take the total, which is $250,000, minus the amount that they actually deposited. Okay. Alright, $114,311.88. That's how much interest they earned. Alright, so let's do one more of those. So we got we want our future value to be $1.5 million. And we've got our annual interest rate is 0.095. And it's compounded semi-annually, which means M would be 2. And it's for 20 years, so T is 20. And we want to figure out the R. Okay, so let's put that in the calculator. Alright. So, you can always see what you actually typed in. Oops. Oops. Guess I just... Wait, yeah. Guess I just erased what I just did. That's not cool. Try that again. Oops. Okay. Alright, yeah, so there we go. Okay, so I had to hit enter. Now I can see everything that I had typed in to make sure that it's correct. And so it gave me $13,195.12. Okay. Alright, so how much of that came from deposits? How much of that 1.5 mil came from deposits, and how much came from interest? So, deposits equals $13,195.12 times 2 times 20. So that gave me $527,804.80. Okay, so that's how much is actually deposited. And then the interest would be the total amount minus the amount that was actually deposited. $972,195.20. So this person really like tripled their money almost. Okay, number 5. If Bob makes his first $1,000 deposit into an IRA earning 5.9% compounded annually on his 25th birthday, and his last $1,000 deposit on his 39th birthday, which equals 15 deposits. With no additional deposits, how much will be in the account when he retires at 67? Okay, so we've got R is 1,000. That's capital R for the payment. We have the little r for the interest rate is 0.059. And it's compounded annually, so M equals 1. and it's for 15 years, so that's T equals 15. Alright, so we're going to calculate the future value. Alrighty, so let's calculate that. Alright, so that gave me $23,099.45. Okay, so that would be how much is in there whenever he's 39. Okay, so then he's just going to let it sit there until he's 67 without making any more deposits. So if he's not making any more deposits, then we're just going to use the compound interest formula that we used in section 5.1. Okay, so that one is used when no deposits are made. So that one was A equals P times 1 plus I to the power of n. And so in this case, this would now be the P. Alright, so now we still have the same R, the same M, but now T is going from 39 to 67, so the new T would be 67 minus 39. So that's going to be 28. Alright, so so let's put that in the calculator. Oops, forgot my multiplication symbol again. Oops, I need a parentheses right there. Alright. Alright, that looks good. So there we go. So I've got $114,000, $114,997.53. Wow. That's a lot. Alright, so yes, this is why we need to start saving up our money. Not that it's easy to find these kind of interest rates, but still. Alright, so number 6 says, suppose Mary wants to start a college fund for her son. If she starts when her son is 5 years old, how much must she put in the college fund each month to end up with $30,000 by the time her son is 18? Suppose 5% interest compounded monthly. Okay, so this time we're trying to find R. We want the future value to be 30,000. Alright, and we have the interest rate is 5%. It's compounded monthly, so M is 12. And the time is from 5 to 8. So 18 minus 5 is 13. Okay, so we're solving for R. Alright, so I think that should be it. So let's plug that into the calculator. Okay, so that gives me $136.92. Alright, so that's how much she needs to deposit. Oh, 92 cents, sorry. 130, oh yeah, I switched my 6 and my 2. 136.92. So that's how much she would have to deposit at the end of each month to save up $30,000 for her son's college fund. That's if she starts at age 5. Alright, so that's it for section 5.2. Thanks for watching. Let me know if you have any questions.